Hello, my name is Ilia Rodionov and I'm a delivery manager at MLabs. Welcome to the close-out video on CEMScript project. In this video, I'd like to talk about what CEMScript project is, how it works, and how one can use it in their work. As the developers of DApps on Cardano, we know that we have to repeat ourselves many times. The very same logic appears again and again within on-chain implementation, within off-chain code, within test suites, and finally within indexing stuff. So we asked ourselves, can we probably generate all these things automatically from the only one description? And it turns out that in many cases we can. And this what CEMScript is actually. This is a framework for building applications on Cardano by providing a description of the corresponding state machines. Let's begin. Before we dive into details, let me give you some useful links. First of all, CEMScript is available under MLabs Haskell account on GitHub. In Docs folder, you can find two important documents: Goals and Design. This document presents the idea of CM, covers its high-level goals, talks about the scope, and considers many cases of DApps we studied. Also, it talks about the existing solutions, including IOG, Bluetooth Application Framework, Genius Hills Atlas Maps, and others. Finally, it presents the core architectural principles of CEMScript. Now, the next document is Getting Started Guide. Here you can find information how to use CEMScript in practice. And I think we will cover most of this guide in this video. Also, you can read an article on MLabs website about testing applications on Cardano with CLB emulator, which also talks about the testing using CEMScript. Finally, you can get to the Catalyst website to get more information about the proposal and the milestones we completed. So first of all, we have to understand how to decompose the whole application. Whole application can consist of many scripts, and possibly we'd like to use several of them in only one transaction. CEMScript takes a very pragmatic approach here. We model every script separately, and if we want to combine them somehow, we can always do it at the transaction level. So, for every script, and here by script I mean spending validator, we define a CM machine that corresponds to this particular script. So now, what is a CM machine? CM machine is a specific type of state machine that can be thought of as a function that takes the current state, then takes some input, presumably in the form of a redeemer, and gives you back a new state along with some list of constraints. We call it TX constraints. So basically, to define such a machine, we need to specify what possible states are and what possible transitions are. And for every possible transition, we have to define a list of constraints. So this is exactly what is done within type class called CEMScript. This type class defines the core thing called transaction spec. And if you take a look at this type, we will see that this is a map that goes from transition to a list of TX constraints. As we can see, this map uses not the transition but its spine. Why is it the case, and what is spine? Well, it's a very simple concept, and it's just the corresponding data type that keeps all the constructors, forgetting all their content. And it turns out it's very useful when you just need to know the type of the constructor, but you don't care about its content. For example, if you just need to pattern match over a particular possible cases. And for this, we provide Haskell, template Haskell machinery to generate such data types automatically. We have two type classes. First is hasSpine, which is a based type class that introduces that spine associated type. And also we have hasBluetooth spine, which additionally brings some compatibility with Bluetooth data. As you can see, it additionally requires toData from data and unsafe from data on the underlying data type. Now let's get back to the CEMScript. So in addition to transition spec I mentioned, there is also transition comp. What is that? This is a way to wire an arbitrary Bluetooth computation into your script. So in cases when you can't use DSL to perform some complex logic, for example, you can do some kind of computation that you cannot express using constraints we support, you always can do that, and you can just run those computation and check the value it returns. We will cover this shortly later on, and also you can see an example for a voting application within the repository to see how it can be used. Now let's take a look at the additional constraints CEMScript imposes. And let's start with the CEMScript types. So this is an additional type class, and it introduces core data types that is associated to a particular script. So script is a type variable here, and basically it's an inhabitant type that just ties together all the stuff that belongs to a particular script. So what do we have here? First of all, two first types here, params and state, are parts of the datum. Params is an immutable part, so you can just initialize it in the very beginning of the lifecycle of a particular script, and this data consists an immutable part of the script datum, and the state effectively represents the current state of the state machine. Now, transition just represents by different constructors of a particular type, and those constructors cover all possible transitions. And here, when we define transition, we don't bind them with states. We just define possible transitions, and we define data that should be provided as an input. As we remember, we defined our function for CM state machine as a function that takes state and input and gives you a new state, right? And for this, we need to do this separation between transitions and states. Now, transition comp is the type we already seen, right? It's used in the CEMScript type class to represent the possible additional computation, namely the result of that computation. And finally, we can see here that by default, this computation returns nothing, void type, and it means that you cannot use it if you don't define it to a different type. Okay, so now we know something about associated data types. Let's get back to the core definition of the CEMScript in transition spec method, represented by CEMScript spec. As we remember, it's based on the text constraint data type, and this is the main and the most important data type within the DSL. So let's take a look at its constructors. So first of all, UTXO constructor allows defining constraints related to transactions inputs, reference inputs, and outputs. So here we can specify the type of the UTXO, and we have to specify the particular specification. We will talk about different types of such constraints later, but now let's just say that to addition the specification represented by UTXO data type here, you also can specify a value that UTXO should have. Ignore for a moment that DSL value resolve script wrapper, just pretend it's a value. Now, the next possible type of TX constraint is main single coin select, and it conveys the idea of someone identified by pubkey hash here spending or receiving a particular value, or doing that at the same time. So you can specify empty value in the case you want to indicate that this value is nothing. Now, the next constraint is very simple. It's called main single no value, and it can be used instead of the main single coin select in the case when both values are empty. So it's just slightly simpler constraint. Then it can be an error, and it turns out being very useful when we express your logic. Next, it can be a condition. So you can combine two constraints for then block and for else block. So TX constraint is effectively a recursive data type. By patterning over something, and again for a moment let's forget about this DSL pattern resolve script wrapper around something that is bool. We will cover it in a moment. Next, something similar, but based not on a Boolean value, but rather on a arbitrary algebraic data type. So here we can match over a constructor and decide what to do. And here again, spines come in very handy here, because we can use spine to represent a list of constructors of an arbitrary data type. And finally, no op constructor, that is also proves to be very useful, especially when we compile constraints. Okay, now let's get back to the UTXO constructor. We mentioned that this UTXO data type represents possible constraints we can impose on any UTXO, right? And in addition to this value that should be contained in the UTXO, we also can use one of the constructors of UTXO data type. Let's take a look. So here we have two constructors. The first one, user address, represents the case when a UTXO is controlled by payment key provided as an argument, which is a pubkey hash wrapped into something that lives inside our DSL, or it might be an own UTXO held by the CEMScript. And this same script argument is a wrapper around something that is a state. So we can express the condition like we expect that that transition should have an input that belongs to our script, and the datum in it represents a particular state. And the same goes for output, so that way we can change the state during transitions. Okay, so now we have covered TX constraint. We saw that in many places we use something that is called DSL value resolve script of something, or DSL pattern resolve script something. What is that? Turns out both are type families, and for our purposes now we can pretend that it's just constant DSL. So let's ignore these two branches when resolve data type parameter equals true, and consider constant DSL data type. It's a generalized algebraic data type, and values of constant DSL represent terms that can be passed to transaction constraint data type we saw before. Here we have several constructors. First of all, constructor ask that allows accessing the context. If we take a look at this CURL type family, we can see that we can access scripts parameters, scripts state, the transition we're currently handling, and that transition comp value, which, remind you, represents the value of our arbitrary computation we can inject into every script as an additional measure. So let's move on. The next constructor is onChain, represents a value of type bool that tells us whether we run something inside an onChain script or within our offchain code. By using it, we can skip some computations that we might not want to run on-chain, because not all constraints that are needed to build a transaction should be checked on-chain. Some of them can be skipped, as we will see later. Now, the next three constructors have to do with deconstructing or constructing values. GetField allows getting a particular value, and unsafe of spine allows building a value by getting a spine and a set of setters. The last one is used more like record field equals value syntax in Haskell, so you can take an existing value and you can just tweak some fields within that value. Now, anything is something that can be used to do some dummy equations and stuff like that. It's mostly needed for technical reasons, and end user shouldn't use it. Eq constraint allows comparing two values, and lift Plutarch and lift Plutarch 2 constructors allow lifting a function written in Plutarch of one or two argument within our DSL. That's mostly it. So getting back to the DSL value and DSL pattern type families, we can see that when resolved data type changed from false to true, DSL values just become value. So we basically just compile them. And DSL pattern becomes nothing, which means that we eliminate them completely. How is it possible? The thing is that resolved parameter is used only for off-chain pipeline. It's not used within on-chain, because in on-chain we always compile a script as it is with all possible branches for all cases, because there is only one script. But when we run our off-chain code, we can always decide what path should be executed, because we know at the moment of execution we know all the state. So all patterns, all if statements represented by DSL pattern can be computed during the preparing or compiling the constraints when we are building a particular transaction. This is how DSL value is different from DSL pattern. And if we get back to the TX constraint data type, we'll see how it's used. So for all cases when we just need a value, we use this DSL value like this, like for value or for user or for value again or for the pub key hash signature, right? And here for if condition, And for match by spine condition, we use DSL pattern. Okay, so now we have seen all parts of our DSL. We are almost ready to get to an example. But before doing that, I'd like to show you a smart.hs module, which contains different helpers and different smart constructors that is supposed to be used in real definitions instead of raw constructors we saw before. So here we have a lot of stuff, starting from simple wrappers for constructors and their specifications. So here we see a general ask and specifications for parameters, for script state, for our computation, then lift to lift constants. Now some helpers for representing an empty value and mean ADA value and all that stuff. Pretty big number of helpers here. Also, we provide some operators, some infix operators to do equations and some comparisons on values. Here, by the way, you can see how we can lift a Plutarch function of 2 arguments into our DSL. And this can be done with arbitrary Plutarch functions. So in addition to that composition, transition comp stuff I showed you before, when we can inject an arbitrary computation inside our script, we also can do it by lifting Plutarch functions, which is an alternative way of doing the same thing. Probably a little bit more clean. Also, we have stuff like CNOT, which does the negation, and off-chain only, which is a wrapper around this thing. So we say if is on-chain doesn't hold, we can run our constraint. Otherwise, just do nothing. This is why no constraint is useful. This helper allows us indicate an error if a particular value is true. Otherwise, do nothing. And also we have some constructors to wrap constraints of type UTXO, like input, like ref input, like output, just to simplify things and make definitions more readable. Okay, so I think most of those constructors are self-explaining. Own UTXO, signed by, spent by, and so on and so forth. So we can go ahead and take a look at our first example, which is going to be an auctioning application, which is very simple, but at least it represents the whole process. So what do we do to actually define a state machine within CEMScript? First of all, we introduce a tag, an uninhabited type, just to tie all parts together. Then we should produce data types for states and for params. And here we need an auxiliary data type called beat in our case, which represents a beat and contains information about who played that beat in field bidder and beat amount. Since we are going to use this type within state and transition data types that should have instances of hasSpine, or more specifically hasPlutoSpine, we need to derive PlutoSpine for this auxiliary type as well. Now, what about states? Our states are very simple. Initially, our auction happens to be in non-started state, then we move to the current beat, and when doing so, we are placing an initial bid by the seller, and finally, we can step over this current bid for many times, and finally we can switch to the winner state, where this bid represents the winning bid, and in this case the current bid in the current bid represents the last bid. Simple auction params is type for script params, and here we have seller and the lot itself. Pretty straightforward. Now transition. Transitions are unbound from states, as I mentioned in the beginning, so we just list them along with some argument that is needed to perform a transition. So for create, for start, for close, and for buyout transitions that are pretty self-explaining. We don't need any arguments, so we can just execute them. But for make bid transition, we need an argument of type bid, because we are placing in new bid. And this is captured here. So now we can define an instance of CEMScript types. And here we're specifying params, what is our params, what is our state, and what is our transition data types. By calling this template Haskell code, we are deriving all necessary instances for these types. Okay, so now we can define the instance of CEMScript itself. Let's keep some auxiliary definitions here. We can get back to them later when we need it. And let's take a look at the map we return in that method. So remind you, it's a map from transition to set of constraints that those transitions should follow. How can we read it? For create transition, we require two constraints to be checked. First of all, someone who is seller from script parameters should spend at least min loveless ADA and get back nothing. It means that we don't care about the change, but we require something should be spent. Now, the output should exist such that it belongs to the script with state not started and auction value in it. Here we start wiring states and transitions, and here is the transition, the initial transition, which takes us from a void state of nothing, like initial state, which is absent in this state machine actually, to the first real state, which is called not started. Now let's take a look at the next transition. Here we say, okay, there should be an input, an own input actually, in state not started, and it should contain auction value. Now what's auction value? This is min loveless plus lot from script parameters. Fair enough. Now we say, okay, there should be an output, an own output, which is logged at our script in state current bid, and the bid field should be equal to initial bid. What is initial bid? Initial bid is that declaration here. So we say that, okay, please build something, some value of type bid out of its spine and some setters. So we say it's make bed spine, and here is setters for all possible attributes it may have. So we say that initial bid is a bid made by seller and the amount is 0. Okay. Also we require that this output will bear that auction value inside. And also we say this transaction should be signed by the seller. And here we see that this start transition takes us from not started state to current bid state. This is the only way how this transition can happen. Now finally, the most interesting transition, buyout transition. And its complexity is dictated by the fact that the initial bid might be the only bid over the course of the auction. And we should handle this case separately. Obviously, we ask for an own input in state winner that holds the auction value. But then we say, if the seller and the bidder are the same person, we just require a seller's signature, which makes sense. Otherwise, we require a bidder to spend bid amount of the bid he played plus min loveless Ada. We don't care about what he gets back. Mind you that that constraint is masked with off-chain only constructor because we don't actually want to check that on-chain. On-chain we don't care who actually pays bid amount. It might be someone else. But for off-chain building of a transaction, we need that information. But this transaction can be built in a different way. Now, we require that there always should be an output that goes to bidder, which can be a seller, with the auction value. We have to preserve the auction value. And only if seller and bidders and the bidder are not the same person, in that case we require that that should be an output to the seller with the bid amount. Because otherwise, if the seller and the bidder are the same person, obviously this output shouldn't exist. So in that elegant way, we can define the whole application logic once, and we can get the implementation for on-chain script, for off-chain logic, for the state diagram, and for indexing out of the box using CEMScript machinery. Let's start with on-chain compilation pipeline. In CEMScript, we use Plutarch DSL to produce on-chain scripts. In onchain.hs file, we can see another type class called CEMScript compiled, which is based on CEMScript and provides a method called CEMScript compile, which takes a proxy of our tag data type and gives us back the whole script we can use on chain. We don't have to implement instances of this type class manually. Instead, we can use our template Haskell machinery, and this machinery under the hood uses generic Plutarch script function defined here. Let's take a look at its signature. So we see it takes the specification of our transitions and additional computation we mentioned before. Remember, in dsl.hs we have that transition comp as a member of CEMScript type class, which defined as a possible function from script's parameters, script state, script transition we are handling, which produces something of type transition comp script. So here we can see the very same signature expressed in terms of Plutus.x compiled code data type and arguments being represented as built-in data. And this function, generic Plutarch script, can give us back a closed term that looks exactly the same as a spending validator on Cardano. So basically our validator. How is done? Well, we use a standard Plutarch technique of hosting a function written in Haskell called main here, which operates over Plutarch terms. And this function is defined as follows. So we use monadic style here, and first of all we are extracting transaction info from the transaction context. From the transaction info we can get the own address of that script, and also from the redeemer we can extract the index of our transition, which is called spine index here. Now we have to handle our arbitrary computation somehow. So it might be present or it might be absent, but we want to handle both cases in the same way, and here we use pdelay to introduce some laziness. So in the case the term is actually present, we can just import this term and apply it to parameter state and redeemer, or otherwise we throw an error. And until a user tries to access the context to get that result of that computation, it's okay because the whole computation is delayed. If user tries to access the absent result, the error will occur. So now we need to build something that can do the job, and it's basically a function that takes our transition or the spine of our transition and returns the p unit as a term, as a Plutarch term. And this is done by per transaction check function. And once we have that computation, we invoke another function which is called compiled spine case switch. And we pass the transition index and the function to run all checks. Let's take a look at those two functions in detail. Okay, so the first step is to build that function that takes a spine of a transition and returns the term of p unit. And we do that by first looking up in our map of possible transitions, trying to find the corresponding transition and extract all text constraints that are defined for that particular transition. And once we have those constraints, we want to turn them into Plutarch terms. And once we have Plutarch terms, we can combine them. So it's done obviously using folder function and compile conster function that turns constants into terms of pbool. We combine them using pend, and we're starting with true. And once we are done, if all constraints are met, we run some additional checks, or otherwise we throw an error. So how do we compile constraints? Well, this function is written in a pretty straightforward way. So we just iterate over all possible constructors, and we produce a corresponding Plutarch term for every of them. But remember, many constraints take also some arguments. So we have also to compile them as well. And this is done by compile DSL function that does the similar thing for constant DSL data type. It iterates over all constructors and it produces the corresponding terms of type pdata. And the last bit here is that check DSL function that allows comparing or testing a particular terms of type constant DSL against an expected value of type term pdata. It handles several cases. Anything is a trivial case, unsafe of spine is a special case, and the standard case is just when we are evaluating our term using compiled DSL testing and just tries to compare it to an expected value using Plutarch equality operator. So once we have that term, that very big and long term, we can run it, and for this we call that compile spine case switch function defined down below, and its existence is justified by the fact that we have only spine index, and in order to run an actual function we have to extract the spine itself. So this is what that helper function done. Nothing interesting happens here, in fact. So it tries to find the corresponding spine for the spine index and finally call that function on that spine, and that's it. So common checks function I mentioned earlier currently checks that staking features are not used because we didn't intend to support them in any way, and that check is done here in the case of checks from our specification are met. So this is how on-chain machinery within CEMScript project works. Now let's take a look how off-chain compilation pipeline works. In offchain.hs module we can find the main entry point for off-chain pipeline, which is called resolve.jx. This function takes a specification for a particular transaction and tries to build it, returning either an error or a fully resolved transaction. Let's take a look at those types. TX spec type contains a list of actions. As I mentioned, CEMScript operates on the level of the whole application when it comes to submitting transactions, but it operates on the level of scripts when it comes to defining state machines. So transaction spec is a definition of a transaction, and we can combine several scripts in one transaction. This is the reason why we have here a list of some CM action, and under the hood this type contains CM action, and CM action is a transition that we want to execute for a particular script. And additionally we pass parameters here. Okay, so let's get back to offchain.hs and take a look at the resolve to X. So this data type, as we can see, represents a transaction that is ready to be submitted. How do we do that? Well, the very same monads.hs introduces several monads, and one of them, called monad submit.jx, allows us to submit a transaction represented by that data type, returning either a submitting error or a transaction ID from Cardano API types. Okay, so this resolve to X function effectively bridges two worlds together, the CM world and the external blockchain world. So how does it do that? Let's take a look. So to do its job, that resolve to X function uses an intermediate representation called offchain to XIR. Let's take a look. Constructors of this data type represent different parts of the target transaction: inputs, reference inputs, outputs, and additional signatures. So our first step is to compile down the definition of all actions within our TX spec into a nested list of such constraints. Once we have all needed parts, we can construct the final transaction, keeping only unique elements. So this step is pretty straightforward. We just iterate over the list and build the resolve to X. Because resolve to X generally is a monoid, we can do it pretty easily. But how do we do the first step? This is the most interesting part. And this is the duty of that resolve some action function here. So let's take a look. So first of all, let's notice that it works in the monad M wrapped into accept transformer, and monad M here is monad query UTXO. So it means that we can ask our UTXO state. Why do we do that? Well, it's needed because we need not only to compile our off-chain specification, we need to run it, right? So it doesn't make sense to, as opposed to on-chain logic when we have to produce a term to evaluate some results. Here we are interested in building a real recipe, which means that we have to run it. And effectively it means we just need to interpret it, right? We don't need to build a big term that can handle all cases. We already have such a term, in fact, so we just need to specialize it according to a current state, which might be absent. It's called M state here because in the very beginning and only in the beginning we don't have any state, and we pass that state to that compile action constraints function belong with the action. And if we take a look at the signature, we can see that being given the maybe state, the same action we're executing, and a CEMScript compiled, this function gives us a list of compiled constraints. We can see that the first type parameter here is true. Remember, it's called resolved, and it's used only within off-chain realm, and it represents the state of the list of constraints. So initially they are TX constraint false, and once we are processing them and once we are executing the logic, in fact, we are changing this type parameter to true, evaluating all values and eliminating all branches. Okay, so let's take a look how this compile action constraints function works. Since we have CEMScript compiled constraint, which means we have also CEMScript type class because it's a superclass, we can use transition spec to get the list of all uncompiled constraints that correspond to our transition. And the transition we can extract from the action. Okay, now once we have the list of constraints, we can try to find the expected state represented by X spine variable here. And this expected state can be defined by a constraint that describes an on-out input with a particular state. So this is the expected state that we expect to see, and we check that the real state passed in this mState argument is actually what we expect for this transition. And we throw an error if they don't match. Now we combine together parameters and the state. This is our datum effectively. And now we are ready to compile every constraint in our list using this compile constraint function. Once we are done, we are handling that list, and we throw an error if one of the elements is left, or we just return the result. So the last bit we haven't covered is that compile constraint function. And this is where we actually iterate over all constructors and decide what to do. So this function takes all context, the datum, the transition. So this function actually knows everything about the current state. It takes a constraint, uncompiled constraint, with resolved argument set to false, and it compiles it to text constraint true. So for every constructor we have specific logic here, and of course, as in the case with on-chain compilation pipeline, we also have to evaluate DSL values. And DSL values are related with this compile DSL function, which also takes all the context, because again, to evaluate values, we have to know the current state of our machine and the transition as an input for this machine. In the next section, I want to touch on the topic of testing. A test suite contains different types of tests, and I'm not going to cover regular tests that just execute a predefined sequence of actions against one of the examples. Instead, I'd like to focus on the model-based testing we're using to verify that our internals are implemented correctly, but the very same types of testing can be also used to verify that a particular definition of a CM script or a CM machine is consistent. I also invite you to read an article on MLab's website called Testing Applications on Cardano with CLB Emulator. There you can find more information about the way we exactly do that, including mutations we use on the level of constraints. Let's begin. In this module, we define two important instances from QuickCheck Dynamic. The first is state model that represents the model, and model is built around off-chain machinery. So we define an associated data type action. It just wraps the transition in this constructor, but also contains additional constructors we use to set up the machine for testing. Now, arbitrary action is an action in gen monad from QuickCheck, and it can generate arbitrary actions based on the available options. And to differentiate between actions that make sense and that don't make any sense, we use this precondition predicate. So this precondition predicate, being granted the current state and the action, tries to compile the constraints from the definition of the machine. If we can compile under some assumptions, we can say that, okay, this action makes sense. Or otherwise, we can say it doesn't. So using this predicate, QuickCheck machinery can generate different sequences of actions that are meaningful to our model. Now, finally, next state function allows stepping model. So by just applying the corresponding transition from our definition. The second important instance in this module is an instance for run model type class. And this instance gives QuickCheck Dynamic machinery instructions how to run the very same actions against a real system. So it consists of only one method called perform, and this method takes the state, the action, and returns something pretty complicated, so I'm not going into details how it's done due to some complications within QuickCheck Dynamic types. But effectively, this method allows running the very same actions in form of real transactions against a real implementation, which is our generated on-chain script deployed within CLB Cardano emulator. So another important topic I'd like to mention is mutations. So we decided to leverage the fact we have the meaningful description of our transitions to apply mutations. So instead of applying mutations as it's done usually at the level of transactions, when we just have inputs, outputs, signatures and stuff like that, we can try to apply mutations on the level of constraints, which is much better, because in that case mutations turns out to be meaningful, not just the random mutations of the transactions, but the absence of important constraints that should ruin everything when being removed. So we introduced some additional types and functions to introduce mutations and to decide whether it's mutation negative. Basically, we test two different types of mutations. So we try to remove constraint, and in that case, everything should fail. Otherwise, our definition isn't consistent. It contains some unnecessary constraints. Or also, we can try to shuffle constraints, and this type of mutation is basically used to verify that our internal compilation pipelines work consistently, so the order of constraints shouldn't matter. So by introducing this simple machinery and some additional functions, we add an additional function to the model class, which is called valid failing action. And this is a similar predicate, so it returns a bool for a particular action in a state, and is similar to precondition. And the difference is that when precondition checks whether an action makes sense or not, this function can say whether a particular action should fail. So action may be meaningful, so for example it's a valid transition, but it just misses some of the constraints, and in that case it should fail. So that way we can check that all negative mutations should unconditionally lead to fail in the real system. Let's see how it works in practice. So I'm going to run the whole CEMScript test suite, and it contains not only property-based testing we've just seen, but also regular test, and now we see this regular test for auction specification. We see the size of the compiled on-chain script, and we see different predefined tests and a successful transition flow among them. And now QuickCheck Dynamic is trying to run various arbitrary, pretty long sequences of actions to check whether on-chain and off-chain parts give the same results. So all tests are green, and this test run we used only 100 tests, but usually we used to use several thousands of them. And using this approach we found several internal bugs in our implementation of off-chain or on-chain logic, and as well we found several inconsistencies in the examples themselves. So I found this approach very useful. In the report we also can see that the distribution of different types of action, negative, positive, different transitions, actors involved, and mutations is fair enough, so we can be sure that we covered most cases using this approach. In the final section of our video, I want to talk about indexing. CEMScript framework provides several useful bits for building indexing solutions. We suggest using Aura Cardano tail utility. In the aura.hs file, there is a function that, being given an instance of CEMScript compiled, will give you a ready-to-use configuration for your Aura. That configuration can separate all related transactions. Once you have all those transactions, you can use another function from event.hs called extract_event that can understand transaction in Aura format and recover corresponding transitions from those transactions. Using these two utilities, the implementation of an indexing solution should be pretty straightforward. I hope that now you have pretty good understanding of what CEMScript framework is and enjoyed watching this video. Thank you.